All right, we are recording and it is noon, so we are ready to go. Welcome everybody for being here today. We have our special speaker. Let me bring up his bio real quick. We have Dr. Jens-Erik Lund Snee, and he is a Mendenhall Research Fellow at the U.S. Geological Survey. Dr. Lund Snee is a geologist and a geophysicist who studies tectonics and geomechanics at a range of scales. He received his PhD in geophysics from Stanford University, where he worked with Mark Zoback to develop a new generation map of the state of tectonic stress in North America, with applications to induced seismicity, continental dynamics, and oil and gas and geothermal energy development. Dr. Lund Snee received his MS in geological and environmental sciences from Stanford, where he and Elizabeth Miller studied the tectonic and paleogeographic history of the Great Basin in the Western US. He was previously awarded a Fulbright Fellowship to study the Alpine fault plate boundary system in New Zealand, and his experience includes works for Statoil, now Equinor, as a hydrocarbon exploration geologist in the Deepwater Gulf of Mexico and for the US Forest Service. So thank you for being with us today. I will hand this over to you. We have a question and answer box. So if you guys do have questions along the way, feel free to type into the Q&A box, and then we'll get to those at the end of the talk. I'll pass it over to you.
Okay, thank you, Molly. Please do let me know if there's any trouble hearing or seeing anything here. But it's my pleasure to present in this venue. I think it's a wonderful way to get together and talk about induced seismicity and energy development, structural geology, geomechanics during these ongoing pandemic times. And I'm going to talk about something that I talked about quite briefly during the business meeting for the AAPG PSGD meeting a few weeks ago, together with Peter Hennings and Mark Zoback. And I'm going to elaborate on a few of those things and go in some other directions, largely talking about understanding the state of stress and what that can tell us in terms of managing induced seismicity and understanding prior induced seismicity, and particularly in the time when we're talking about ramping up geothermal energy and carbon capture and storage, in addition to oil and gas development. So this probably won't be a surprise to many of you. I think Mark Zoback has shown this, maybe not this particular slide, but this general idea a number of times in public talks. The consensus among groups, in this case, this is the IEA, International Energy Agency, but the IPCC has similar models. The consensus is that to limit climate warming to 1.5 degrees Celsius, the economy needs to switch by 2050 to net zero emissions. That is an extremely tall order. In that report, they emphasize how much of a tall order that is. For example, if just thinking about 2030, 8 years from now or so, the world economy might be something on the order of 40% larger than it is today, but we would need to be emitting 7% less carbon dioxide at that time. And needless to say, the quote here is quite pertinent. Achieving net zero emissions by 2050 will require nothing short of the complete transformation of the global energy system. I'll emphasize what that means for us as geoscientists here. There's one of the critical technologies that is discussed as a way to achieve net zero carbon emissions, of course, is carbon capture, utilization, and storage. And this is the IEA's breakdown over time and by mechanism of the amount of carbon capture and storage that would be needed to achieve that net zero emissions by 2050. And to underscore the challenge facing society and geoscientists and engineers in particular over the next few years, we are here at about 40 megatons of injection of carbon capture, carbon storage per year right now. And by 2030, in roughly 8 years, we're going to need a 20 times increase in that capacity. So that is a very tall order, and this figure is a little complicated, but each of these little colorful items here represents one of the components of that storage. For example, storage next to coal burning power plants, natural gas facilities, and so on, and then ramping up dramatically beyond that to 2050 and then 2070. What about geothermal energy development? It is a technology that has not been a large player in terms of electricity generation, but it has received a lot of press in recent years, and for good reason, because there have been some impressive advancements in the technology. There's a lot of press around that. You can see here oil and gas companies, large companies like Chevron, have started investing in geothermal development. The technologies have been advancing to the point that they've been gaining attention, but as is emphasized in this Wired magazine article here, the induced earthquake potential is a significant one, and I'll talk a little bit more about that. But geothermal energy has, as I mentioned, been a very minor contributor to the overall energy mix so far. This is, in 2020, about 94 terawatt hours worldwide produced, according to the IEA, in order for it to have, play its role in mitigating the climate change, the increase in global climate temperatures. By 2030, there's going to need to be an approximately threefold increase in geothermal development and power generation by 2030. So that's another tall order. And you can see here just the tiny role that geothermal has played thus far relative to some of the other renewable energies, which themselves are a minority of electricity generation. So a massive ramp up of geothermal energy is also required. And it won't be a surprise to anyone here that there's a lot of opportunity for geoscientists in this future. However, I mentioned the earthquake issue. This is a map kind of underscoring that. I'm showing here the earthquakes that are spatiotemporally associated with geothermal and carbon capture and storage development areas worldwide. The red dots are places where geothermal development is thought to have triggered earthquakes scaled by moment magnitude here. So you can see a few magnitude 5+ earthquakes are suspected to be related to geothermal development. Many people are familiar, for example, with the Pohang event a couple of years ago in South Korea that was quite damaging. Carbon capture and storage has been associated with some seismicity, it's thought, but you can see here that the orange triangles represent those cases where where seismicity has been suspected to be related to CCS, and there's only 2 of them shown on this map, both with earthquakes less than magnitude 2. But to underscore the challenge ahead of all of us, this seismicity profile that we're looking at here is at 40 megatons of carbon dioxide storage relative to the 20 times that needed by 2030. And geothermal will need to increase by 3 times by 2030 while keeping seismicity under control. So with that as a background, I'm going to talk about the understandings that we can gain from having a clear picture of the state of stress, both the orientations of SHmax and the relative magnitudes of the 3 principal stresses. I'll make a few points about stress mapping in general, understanding the stress field and geomechanical considerations, and then I'll move on to talk about the implications for understanding and managing induced seismicity, talking specifically about some learnings that we've gained from the oil and gas industry's experience with induced seismicity, particularly associated with wastewater disposal in places like Texas and Oklahoma. So to get everyone on the same page, one of the wonderful things that I'm realizing about the old days of being able to present in person is that I can sort of judge what my audience is familiar with already and move quickly through things that they know. For the sake of those who don't know some of the background here, I'll just start by saying that in general in the Earth, we expect three general types of faulting. These are the Andersonian faulting mechanics. Geologists will all be familiar with this. And because one of the principal stresses in the Earth's crust is thought to be subvertical, and the other two are, being mutually perpendicular, will be subhorizontal. This offers us some nice simplifications when trying to understand the stress field. Specifically, when the vertical stress is the greatest, we expect normal faults, steeply dipping, extensional faults. When the vertical stress is intermediate, strike slip faulting occurs, and compressional reverse faulting occurs when the vertical stress is the least principal stress. So what you need to know to understand the entire stress field for our purposes in the Earth, at least in a relative sense, is the relative magnitudes of the three principal stresses and the orientation of the maximum horizontal principal stress, SHmax. And we have several ways of doing that. This is a way that is used frequently by the oil, gas, and geothermal industries. Use of borehole image logs to identify wellbore styles of wellbore failure that indicate the orientation of the maximum horizontal principal stress. So these are unwrapped views of a subvertical borehole, and you can see these thin fractures or drilling-induced tensile fractures. Those form on the parts of the borehole wall parallel to the SHmax orientation when they exist, and borehole breakouts, these darker zones, which may or may not occur in a well and are uncommonly associated with drilling-induced tensile fractures, but here they are in the same place. Those borehole breakouts will form 90 degrees away in the orientation of SHmin. So I want to underscore that we employ quality criteria to determine which measurements are considered reliable and good enough to put on a map. And that involves the use of reliable stress indicators, such as borehole breakouts or drilling-induced tensile fractures. There needs to be enough consistency in their orientation up and down a well. There needs to be enough length of their appearance up and down that well to be considered reliable, and there need to be enough of them. So the quality criteria is a critical component here. We have several other reliable techniques. There is, of course, the potential to use earthquake focal mechanisms. These beach balls here, they can be inverted to determine the style of faulting and the orientation of SHmax that would have given rise to a group of them. So we recommend at least 20 focal mechanisms in a localized area can be inverted to provide precise orientations of SHmax and the relative magnitudes of the three principal stresses. And there are some newer techniques that Mark and I have started using. This is one example here. These are aligned microseismic events during hydraulic fracturing stimulation in unconventional oil and gas setting. These are horizontal wells viewed from map view, and you can see the stimulation is happening from the toe to the heel of this subhorizontal well. The dots are colored by the stage of stimulation, and you can see that there are many aligned groups of events that occur throughout here. And in some cases, including this one, these represent the cloud of shear events, micro earthquakes that occur around the propagating hydraulic fracture. So they define the hydraulic fracture orientations. And because the hydraulic fracture opens against the least principal stress, in many cases, we can use it to measure the SHmax orientation if you have enough of them. And new data sets have improved considerably from here. This is a few years old, but you can still get the picture. Okay, so let's just move ahead and look at the results. This is the new map that Mark and I created. We're calling it a new generation map of the state of stress in North America, and I'll explain why that is. For one thing, we've added a few hundred new SHmax orientations to the map. So those are the black lines here. We're using the world stress maps, SHmax orientations, as well as our new ones. And you can think of each of these lines as a point measurement, usually a wellbore, sometimes a microseismic project area. And the line points in the direction of the maximum horizontal compression, SHmax orientation. So let's say up here in the Bakken area, we're in northwest North Dakota, we're looking at northeast southwest SHmax orientations. The length of the line corresponds to the quality of the data. So we're showing only reliable quality on the map, and the longer lines are A quality data, our highest quality. And so a few things become apparent quite quickly. In the northeastern US and eastern Canada, you see that SHmax tends to be northeast, southwest, and there's a gradual rotation southward and westward into the interior parts of the continent towards closer to east-west. You can see that in Oklahoma, where we have a lot of data. It's close to east-west orientations there. Texas, as we'll discuss later, shows a lot of variability in SHmax orientations, but they're coherent. And we'll get into that shortly, but you can see that expanded here. Areas that look quite chaotic at this scale, if you zoom in, tend to look coherent. And you can see in the western parts of the US, there's a lot of variability over short scales in SHmax orientations. Here in Western Canada, closer to northeast, southwest SHmax as well. The thing that is particularly new about this is that we are now mapping the relative magnitudes of the three principal stresses. That's the colored background. We're doing it using the AFI parameter developed by Bob Simpson at the USGS in the 90s. And that is a clever way of using a single number, which ranges from 0 to 3, to represent the ratio of three things, those being the three principal stress magnitudes. So these are not absolute magnitudes, these are relative magnitudes. And the cooler colors represent lower AFI or more extensional settings. Green and yellows represent strike-slip faulting, and reds represent compressive reverse faulting all the way up to 3, which is the most compressive case. And so we can expand the normal Andersonian faulting theory view that I showed a moment ago to include all the types of faulting that can occur with one another. And so you can have both. You can have the Andersonian cases in the central column here, but there are additional cases as well. The most extensional possible is radial extension. It would be AFI of 0, where normal faults of any strike orientation could be active, quite rare in practice. AFI of 0.5 is normal faulting, blue on the map. A little more compressive, strike slip and reverse faulting occurring at the same time. That is anything greater than 0.5 and less than 1.5, say 1.0. This can be misinterpreted as when normal faulting and strike slip faulting are occurring in the same areas. It can be misinterpreted to suggest a very complex stress field, but much more likely is that we are seeing a hybrid normal and strike slip faulting stress regime in that area. And we see a lot of that. You can see these teal areas, for example, in Western North America, which dominate large parts of the Western conterminous US in particular, are strike slip and normal faulting. Pure strike slip faulting is AFI of 1.5, and then we continue to get more compressive through strike slip reverse faulting all the way up to radial compression, which is again a rare style of faulting of AFI of 3. Knowing this, we can I'll just make a few very first order observations about what we see on this map here. The eastern part of the continent is compressive with reverse faulting along the eastern seaboard and eastern Canada in the Hudson Bay area. Moving to the west, the style of faulting becomes less and less compressive. We transition through this orange area of strike slip and reverse faulting at the same time, and transition to the green area of strike slip faulting. The transition, you'll notice, doesn't occur uniformly depending on latitude. And Oklahoma, for example, is a lot more compressive than the areas around it, with dominantly strike slip faulting, but also some normal and reverse depending on where you are. And then the Western US, as I mentioned, is more extensional. So with this in mind, I'm going to make a few points about how to understand these maps and a few pitfalls to avoid, and then I'll talk about induced seismicity. Looking here just at the northeastern US, this is the area that's compressive, transitioning from reverse faulting on the east here to almost pure strike slip faulting on the west. The Utica and Marcellus play outlines are here in the Ohio, Pennsylvania, New York, West Virginia area. And we have a lot of SHmax orientations, both from the world stress map and recently added by us in this area. And a point I want to make here is that not only are these orientations consistent and coherent in space, you can see that they tend to agree quite closely, but they also agree with each other regardless of the stress indicator that is used. So they're symbolized by different types of stress indicator. Drilling-induced tensile fractures and borehole breakouts, wellbore measurements I mentioned first, are shown by unadorned lines. Aligned groups of microseismic events defining hydraulic fracture have the outward pointed triangles. The focal mechanism stress inversion, SHmax, derived SHmax orientations have the circle over the line. And then there are geologic indicators and other types with the box over the line. And you can see the consistency that they show between different types in this area. Incidentally, I'm pointing here at an area studied, an oil and gas development area, studied by Gator Lawley and Mark Zobak, that occurs right at the transition between strike slip and reverse faulting. You can see the orange color there, AFE around 2.0. And that's actually where we expect hydraulic fractures to transition from being vertical, as we often think of them as being, because they open against the least principal stress, which is SHmin in extensional environments and strike slip faulting environments. But they transition here to hydraulic fractures that would open vertically. Would open vertically and be horizontal. And in fact, and that's what we expect with compressive environments, because in those environments, the vertical stress is the least principal stress. And in fact, Lawley and Zobak see that in this particular area, where depending on the lithology, they see some hydraulic fractures developing horizontally and others developing vertically. And I won't get into the specifics of why the lithology matters, but they're right there at that transition, just as we would expect. So another point to make is that the stress field, I've already made this point, but it's spectacular to see in Texas, particularly in the Permian Basin here. The stress field is coherent even places where it's complex. So if we zoom in on the Permian Basin here of West Texas and Southeast New Mexico, you can see this remarkable change in SHmax orientation across the Delaware Basin, about 150 degrees clockwise from north to south. There's other variability happening in places like the Northwest Shelf and down here in the Valverde Basin, much more consistency in orientation over in the Midland Basin and Central Basin Platform. We've added most of these data, and I'll say that if we had 1/10 as much data, we would probably be very concerned about the apparent chaos in the pattern. But with this much data, it's clear that there are smooth trends happening. Different types of indicators agree with each other in orientation, and this can be mapped coherently. This is an extensional area, by the way. You can see the Rio Grande Rift is right at the margins, and these blue lines represent active, quaternary active normal faults from the USGS database. Okay, another point is that when we're looking at these maps, I get asked about this a lot, we're looking at information that usually represents the stress orientation for the entire brittle crust, not just a particular depth, even though the measurements may have been collected over a narrow depth range. And that is shown very nicely for these areas here in the Denver Basin and Uinta Basin of Colorado and Utah. Most clearly in the Denver Basin here, where we see this quite apparently sharp change in orientation from about north-south SHmax to a closer sort of west-northwest, east-southeast orientations, going from the blue measurements to the black measurements. And the consortium that used to fund me, during one of the meetings, one of the operators asked, how are you sure that that's not a rotation with depth that just looks like a rotation happening over space? So we looked into that because this is quite an interesting pattern here. And it turns out the results of that you can see on the right in this sort of graph here of the depth of measurement as a function of the SHmax orientation. And so with the black measurements, you see a fairly consistent set of, about north 100 east or so SHmax orientations, but we don't see any indication that there's a rotation as you move deeper. In fact, there's an overlap in depth ranges between these very different SHmax orientations. So it does appear to be a change in stress orientation laterally, but not with depth. We see that also in the Uinta Basin, where there is a little bit of overlap in depth, but it's clear that there's no systematic rotation happening in depth there. Okay, and sort of, I think there's a final point, is that the strain rate and stress fields are not the same thing. They can be confused. I have seen this happen a few times where the stress orientations are assumed to be the same as the orientations of principal strain rate, but that is not necessarily the case, as shown spectacularly here. This is the active strain rate in the more stable parts of North America, as measured by Corney Kramer and others a couple of years ago. And so here's Hudson Bay. And what they're seeing is the signal of surface deformation associated with post-glacial rebound following the removal of the Laurentide ice sheet some 10 or more 1,000 years ago. The color scale here is exactly the opposite from the stress map. So the areas that are red here are undergoing dilatational strain, so spreading apart as they lift up under the areas of formerly thickest ice. And then there's a sort of zone around that that's blue that's undergoing active contractional strain on the surface. And that's around the margins of the former ice sheet. And we have almost the exact opposite pattern in the state of stress, where in that area around Hudson Bay, we see reverse and reverse strike slip faulting, and then it becomes generally less compressive to the south and the west away from that. So an important caveat there. Okay, moving more in the direction of induced seismicity and how to apply these measurements and principles to that, I want to make an important point here first, that the crust is almost everywhere thought to be in a state of frictional equilibrium. You could also say that it's critically stressed. And another way of saying that is that the differential stresses, so the difference between S1, the maximum principal stress, and S3, the minimum principal stress, is governed by the frictional strength of the best oriented faults. And that's been shown in several ways. This was formalized by John Townend, Mark Zobak, Balz-Groleman, and others in the early 2000s. It's been shown through borehole stress measurements, where, in some of these deep research wells, where the magnitudes of S1 and S3 can be measured fairly precisely, as well as the pore pressure. And it turns out that the ratio between those two tends to lie, as you would expect, along a line defined by laboratory measured coefficients of friction that we expect for faults between about 0.6 and 1. 0.6 tends to be what we expect in most places. You can also see examples of this from reservoir-induced seismicity in stable areas. Here we're looking at parts of North America and Southern and Eastern Asia, where we have the natural seismicity, some of the larger earthquakes shown in the black dots, but reservoir-induced earthquakes, or those thought to be induced by reservoirs, are shown with X's. Sometimes those have been quite damaging events that have killed a lot of people. And you can see that in some cases, India, for example, and Eastern China, there are a number of those in areas that are quite stable and subject to very little natural seismicity. And the implication here is that just the small amount of stress perturbation applied on the Earth's surface by that impounding that reservoir was enough to trigger slip on faults that were well oriented, already had a lot of differential stress built up on them, and therefore were likely to fail maybe 100,000 years from now or 10,000 years from now, but were triggered today. So it's important consideration there. Now, one outgrowth of that principle is that we can do several things with it. For one thing, we can actually estimate the absolute magnitudes of the three principal stresses from maps of A phi, which, as you remember, represents the relative magnitudes of the three. So this requires making a few assumptions and knowing something about the pore pressure and the magnitude of one of the three principal stresses. So I'm showing that here. And these are, so the upper plot here is for cases of hydrostatic pore pressure, which is what we expect the crust to experience in most places. And so this is the principal stress magnitudes normalized by the vertical stress. So the vertical stress stays constant here as a function of A phi getting more compressive to the right. So normal, strike slip, and reverse faulting. And you can see that if if the vertical stress stays constant, let's, the equivalent would be for a single depth in the crust. The horizontal principal stresses will increase in systematic ways. And we can use this to estimate at least the bounding permissible magnitudes that the horizontal principal stresses could have for a given pore pressure and vertical stress. And this can be quite useful. But you see, as pore pressure increases, the differential stress, or the difference between the maximum and minimum principal stresses, also decreases. So we've laid out the equations that you can use for this in a new paper that is now out in a sort of preprint form in AAPG bulletin. And just to emphasize, if you have vertical stress measurements, which is fairly easy to measure or at least to infer, then you can estimate at least the bounding magnitudes of the other three. And here's an example from Katie Smye and others from the Texas Bureau, where they've actually made a map of the vertical stress gradient across the Permian Basin. Okay, and this actually brings me back to explaining, just for a moment, taking a detour from induced seismicity to explain the reason why we see this difference between the strain rate and stress fields so markedly in the eastern parts of the continent. And the reason is all about stress magnitudes. It turns out that the stresses stored in the crust already, particularly in an area that's more compressive, as you can see here, are the differential stresses are just much greater, that are already stored in the crust, are just much greater than would be associated with this strain that's occurred since removal of the ice sheet, let's say 10,000 years ago. So using those principles at about 10 kilometers depth, making a few assumptions, we would expect in this compressive area more than 300 megapascals difference between the maximum and minimum principal stresses. Whereas if we take the total amount of stress change or relaxation that would have occurred as associated with the strain that we see in this map since the ice sheet was removed over the last 10,000 years, and making a few assumptions about elastic constants, at 10 kilometers depth, we expect that change to be less than 2 megapascals. So in other words, the stress relaxation associated with this post-glacial rebound is less than 1% of the stresses already stored in the crust. So that is the reason we think why there's such a difference between the stress and strain rates there. Now, back to induced seismicity. This is a Mohr circle. I realized that many people studied those at some point during maybe in a structural geology class and never wanted to see one again. So I will keep this high level. You don't need to understand these things. I'll just say that these are plots of shear stress as a function of normal stress. Usually you'll see effective normal stress, which is the normal stress on a given plane of any orientation minus the pore pressure. So here we're just showing normal stress. And so this is the shear stress versus normal stress resolved on the plane of any orientation. And that's what these black dots are, just randomly oriented planes in a given stress field that you can measure. So this would be the orientation of SHmax here, the greatest principal stress. Vertical stress is a little less. So this is a strike slip normal faulting stress state here, slightly in the direction of strike slip faulting. And because the crust is critically stressed, we expect a narrow range of fault orientations to be at approximately the failure line and just be failing over and over again in geologic time as stress builds up on them due to tectonics and then relaxes and then builds up, relaxes during an earthquake and then builds up back up again. So anything that crosses or touches this failure line, we expect to be within one earthquake cycle of failure. Now, if we increase the pore pressure, say due to wastewater disposal, that has the effect of making more orientations of faults than the most ideal ones potentially active. And so many people are used to seeing the Mohr circle moving to the left as pore pressure increases. That's because that happens on plots of effective normal stress. So this is just normal stress. And so that it's the same thing, but in this case, the failure line is moving to the right. And with enough pore pressure increased in an area, you might end up triggering slip on a fault that may have, that possibly was going to fail at some point in the future, but is failing now. And if you know the orientation of that fault, let's say from a focal mechanism nodal plane, you can estimate the pore pressure to slip that would have been required in that stress state. And so we've tried this in a few examples. This is the famous case of Azle, not far from Fort Worth, here in the northeastern Fort Worth Basin, where two magnitude 3.6 events occurred in 2013, 2014, and it was suspected that they may have been related to wastewater disposal in the nearby area. So we made a map of the state of stress in this area, and we wanted to know, okay, so how well oriented were the causative faults? And here are the causative faults shown by these nodal planes from composite focal mechanisms by Matt Hornbach and others. And you see that there was a normal fault dipping kind of steeply to the northwest, and then there was an antithetic normal fault joining that, dipping to the southeast. And knowing what we do about the stress field there, the teal color on the map represents strike slip normal faulting. So that's SHmax and SV are about equal. SHmax is about parallel to these normal fault strikes. Turns out that both faults were extremely well oriented for failure. And in fact, that antithetic fault was so well oriented for failure that we effectively would have required a very small perturbation to trigger slip on it. So it turns out that, I'm not going to go into other examples. We see this over and over again with cases of potentially induced seismicity. And this has been shown more recently on a grander scale by Martin Schoenbaugh and others for the case of the Oklahoma earthquakes that are thought to be associated with a few factors, largely wastewater disposal into the Arbuckle Formation deep near the basement. And so here is Schoenbaugh and others relocated events. Catalog here, you can see this is central northern Oklahoma and south central Kansas. You can see how many of these events line up on planes defining the causative fault. We know the state of stress. Note the color scale is a little different here, but SHmax is generally about north 85 east. And we have some version of strike slip faulting and or normal and or reverse faulting, largely a little more in the normal faulting direction in these areas. So we can predict the orientations of faults that are likely to be active. That's shown on the outside of this Rose diagram here. These are the red zones, or the strikes of strike slip faults that we would expect to be active. You might also have a few normal faults that would be parallel to these planes, or sorry, parallel to SHmax here around north 85 east. And then inside the Rose diagram, you see that indeed the measured orientations of those faults are very close to what we would expect under Mohr-Coulomb failure theory. This is a strong indication that it works. It's exactly the faults we expect to fail that are failing, and they tend to be quite close to failure. This is a view of the same area here. More recent work by Cornelius Longenbroek and others did pore pressure modeling in the deep rocks in this area. They took the wastewater disposal injection volumes by month, and they did very simple pore pressure modeling, radial diffusion, with, I think, the only horizontal heterogeneity introduced to that model was the presence of this sealing Nemaha fault, so it's a flow boundary. And what they show is that pore pressure increased in a pattern, a spatial pattern very similar, and temporal pattern very similar to that of the earthquakes. So the earthquakes are shown by these gray dots, and the magnitude 4 pluses are shown by these yellow stars. And I want to emphasize how little pore pressure this required according to this model. It's about 0.3 megapascals or so at most. That's about 45 psi at 6.5 kilometers depth. So that's, bicycle tire pressure at 6.5 kilometers depth. Increase in pore pressure is likely associated with most of these earthquakes. Okay. Now, I've been talking in deterministic terms about induced seismicity and understanding the stress field thus far. And I want to emphasize that we can also approach this deterministically. What we're looking at on the left here is our map of uncertainties for the AFI map in our stress map. And the green areas have lower uncertainty, and the purple areas, like you can see in the Canadian Shield, are higher. And so we can take advantage of what we know about the whole parameter space, or about the uncertainties on all of these factors that matter, and use them in a probabilistic way to understand how much pore pressure might be needed to make a fault slip, or how much pressure was needed for a prior earthquake. And we do this using the fault slip potential, the FSP tool from Stanford that many of you probably know, maybe even use. And what that tool does is it has both a deterministic and probabilistic functions to it. And with the deterministic tool, it'll allow you to input, all the ranges of permissible values for each of these geomechanical factors that matter. In this case, vertical stress, the ambient pore pressure, fault orientations, SHmax orientations, AFI, and so on, friction values. And it'll run a Monte Carlo simulation to estimate the range of pore pressure increases that would have been needed to bring a given, this is for a given fault here, to touch the failure line in this case, at a particular reference depth. And so you can do this with many faults, including in a changing stress field. That's what's shown here for the Permian Basin. So we know the state of stress well there. And this is a new fault map by Lily Horn and Peter Hennings and others, the Texas Bureau. And Noam Dvory, Mark Zobak have run fault slip potential here on those faults by their individual segments and shown which ones are potentially hazardous, those are the red ones, in response to, in this case, a 300 PSI pore pressure increase. This is a sort of newer version of a paper that Mark and I published with the older faults back in 2018. So it's quite powerful, both the having access to these types of data, but particularly tools like this for screening, say, an area where wastewater disposal or carbon storage or reservoir stimulation could be occurring for seismicity. But you can see here, the gray dots represent the actual seismicity in those areas. And an important point that that they've made and that we made in our prior paper is that it's very important to know where the faults are. Otherwise, there's not much that you can say in terms of their hazard. So here, where the faults are not mapped, but where seismicity has occurred, are clear indicators of the importance of having as much information as you can possibly have, both about faults and about stress. Okay, so we, with Peter Hennings, we approached this for the Fort Worth Basin. In this case, we tried to solve that problem about not knowing the faults, and Lily Horn and others again developed a detailed fault model for that area. And so we were able to estimate the fault slip potential on those from our stress mapping. And you can see a large number of well-oriented faults shown in red in that area, and the seismicity that occurred largely on those faults. And I'll just mention this very briefly. The point here in these histograms is that it is the faults, the lower one represent the faults associated with earthquakes. It is the faults with higher fault slip potential that are the ones failing in this area. I should mention that seismicity in the Fort Worth Basin is largely thought to have been associated with wastewater disposal, and it's tapered significantly in the last few years. But those with higher fault slip potential, 0.2 up to 0.4, tend to be the ones, as we would expect, that are failing. Very few with low fault slip potential are associated with earthquakes. If you look at the entire, so that's just the faults associated with earthquakes. If you look at the entire population of faults, you see, as you'd expect, a large proportion of faults with very low fault slip potential, but those are not hosting earthquakes. Interestingly, there's a population here with very high fault slip potential, 40, 50, 60% probability at that pore pressure, 1 megapascal pore pressure increase, that fault could be brought to critical stress. And yet there are very few of those that are actually resulting in earthquakes. The most likely explanation is that those extremely well-oriented faults are down here in the southern part of the basin where wastewater disposal was not happening. So there's just no triggering mechanism for those. So we wanted to move beyond having a very basic estimate of, assumption of uniform pore pressure increase at a given depth. And so Rebecca Gao and others at the Texas Bureau developed this very nice pore pressure model based on the injection history in the Fort Worth Basin, all the way from 2005 to 2018. You can see this is a figure showing just the maximum increase anywhere in that time of pore pressure at any given area. So this is the eastern Fort Worth Basin. Here's the Dallas Airport earthquake sequence. So Fort Worth is kind of in this area in Tarrant County, and Dallas is over here in Dallas County, and there's the Irving earthquake. So you can see the groups of earthquakes shown in pink, the causative faults shown in green, and the areas with high pore pressure increase modeled shown in more tan and red colors. Okay, so if we look at those, we see things both expected and that indicate sort of the limitations of our present knowledge. These are two examples, the Azle-Reno earthquake I mentioned earlier and the Cleburne West seismicity. And so the top is the Azle-Reno case, and you can see the solid line is the pore pressure increase over time. That's the same in both of these, pore pressure increase over time. And so consequently, we estimated the fault slip potential due to that pore pressure increase over time. You can see it increases modestly in both of these cases. And just as one would expect, as the pore pressure and hence fault slip potential increase, eventually there is seismicity. In this case, in the Azle case, there's about 45 psi increase. In the Cleburne West case, there's about 52 psi increase at the causative faults. But it's not, there's no clear threshold that we can use in a predictive way to anticipate when earthquakes might occur as a function of pore pressure increase. So these faults had a fault slip potential, in this case, of a little less than 0.2, and it increased at the time of seismicity to a little less than 0.25 in the Azle case. And in the Cleburne case, it was even less than that, a little more than 0.1 up to a little less than 0.2. So it's not clear how one would use that to identify which specific faults of the well-oriented ones might be best oriented for failure. So this, or might actually fail. So we know there are many faults well-oriented for failure, but which ones are actually going to fail remains something that's very difficult to predict in terms of which faults and when specifically. Okay, so I'm going to close by mentioning a few approaches that we can use to better understand the hazard and risk given some of these uncertainties and given the new data that we have. One approach is by, I'm involved with a group of people at the USGS and at the University of Maryland, led by Konstantinos Francis. And what we're trying to do is use our information of the stress fields to improve probabilistic seismic hazard analyses. So this is a fictional example for the Mears fault, using fault slip potential tool, not as it was intended to be used, but as a probabilistic approach for understanding which parts of faults might be most active given uncertainties. And this is just the results of that test study for one scenario in which you can see two different parts of the fault, and due to a number of factors that can be studied, like the localization of the earthquake, where on that fault, based on the fault strike and dip relative to stress, for example, where the earthquake would occur, you can see that there's an appreciable difference between site 1 and site 2, that would be in orange and blue, in terms of the spectral acceleration you would expect as a function of distance away from that earthquake, and in this case, as a function of spectral period. So this is very much in development, but we're hoping to improve PSHA using what we know about the state of stress. I'll emphasize this work by Ryan Schultz and others from Stanford, and they're approaching the risk question from a different angle and showing here ways that if you take what we know, not about the state of stress, but the population information, the near surface seismic velocities, and so on, as a function of the expected magnitude of an earthquake, you can estimate how many people will experience that earthquake as a felt event, and how many households might be damaged given the population density, or if you have a limit to how many households you're willing to allow that nuisance, you can estimate the maximum magnitude that could be allowed at a given project location. So more details about that in this paper, very nice paper in Science about that. And I just want to close by bringing it back to carbon capture and storage in particular, and pointing out one example that I think was done very nicely, where this is the Decatur, Illinois project, carbon capture and storage, where Sherilyn William Stroud and colleagues have done site characterization in that area using all of the information available to them, ranging from the information about the state of stress. We have the SHmax orientation of that area. They use reflection seismic surveys to determine the faults that could be resolved at that scale, how big they are, how well oriented they are. They use borehole measurements to determine the fault orientations in that area at the scale of boreholes, among other factors, as well as the history of regional seismicity. So here's the study site. Regional seismicity tends to be concentrated much further to the south, so it's a little bit lower seismicity in the study area. And from that information, they were able to determine which parts of the faults that mappable scale had higher slip tendency. Those would be the ones in yellow, so more likely to fail as a result of injection of subcritical or supercritical carbon dioxide. And so they've taken all the information they have available and used it in an integrated way to understand what types of seismicity they might be dealing with, including potentially on a worst case scenario. So the largest events they've shown in the seismic profiles in this area are about would have a source radius commensurate with about a magnitude 2.7 earthquake. And then here they've managed to keep seismicity down below magnitude 2 to about the largest is a magnitude 1.6. So this I think gives us a way forward in terms of, or an example of a nice way forward as we move toward potentially having more and more of these industrial processes that involve increasing the pore pressure in the subsurface and hopefully using this information and these principles to manage the potential for induced seismicity. Thank you.
Awesome, thank you so much. That was great. I know these maps get used a lot in industry. I use them a lot, and this was really helpful kind of understanding what goes into them and how they can be used. So I really appreciate it. And we do have some questions. We had a few come through in the chat, and then we also have a few in the Q&A box. If you are able to pull those up, I will let you read those and answer them, but just let me know if you need me to read anything for you. All right.
I think I can, yes, I've got them here. Okay, I guess I'll start with, oh, here's one I didn't, this is a good one to start with. Tim Davis is asking if I could expand on how I estimated the A-phi value. Yes, I left that out. We can do that with earthquake focal mechanism stress inversions. We can do it quite precisely, but of course, earthquake focal mechanisms tend to be concentrated in a few areas that with high strain rates, like along the West Coast. And so most of the time we don't have enough focal mechanisms to do a reliable inversion. So we will use individual mechanisms and use them in sort of an interpretive sense to determine the state of stress. I outline this in more detail in our 2020 paper about this and the one that just came out in AAPG bulletin. But the basic idea is that in an area, if you see, let's say, a normal faulting focal mechanism and have no other information, you know you're in some wide range between radial normal faulting and normal strike slip faulting. But then let's say a strike slip earthquake occurs in that area as well, then you know you're somewhere in the normal strike slip range. So so we can kind of narrow down those permissible ranges. And so it's an interpretive approach. And then we've done that all across the map. There are a few cases where we can use the USGS quaternary faults and folds database to inform that, although the focal mechanisms tend to be a lot more reliable for this purpose. Okay, Jeremy Boak is asking, in the Langenbruch map, in the northwest part, there's a distinct, very dark zone that has no earthquakes greater than magnitude 3 in it. What explanation is offered for that? I think I would refer you, I'll go back to it, but I'll refer you to their paper because I don't think I'll give a great answer relative to what they would say for that area. It could be that the permeability in that area is a little different than what they estimated. It could be that there are fewer well-oriented faults, which would be represented by a lower seismogenic index in that study. So I would have to look at their map of seismogenic index, but that might answer that question. Colin Sayers asking, results are based on Mohr-Coulomb failure theory. Are there observations that suggest limitations to that theory? Yeah, I mean, Right there, it's a simplified way of looking at seismicity and how it can occur. We have to make assumptions about what the friction result on that fault was, and we're not doing rate and state friction. So and it doesn't account for things like pore elasticity that can be framed in terms of Mohr-Coulomb failure theory, but we're not doing that in these cases. But I just want to emphasize how well these very simple approaches work. We can see it nicely for the case of Oklahoma, where the vast majority of faults that are producing earthquakes are ones we would expect to fail. How did I make the maps? I did most of it in ArcGIS with a little help from Adobe Illustrator. Okay, Gary Prost, is the stress field transition always smooth, as shown on the map, or can it be abrupt? And can you get a transition directly from normal to reverse? In other words, can the color scale be circular or continuous? There are a couple things in that. I will just, let's see, I think the best example will be, the best explanation, sorry about moving the slides like this, will be apparent here. For a long time, it was thought that there were stress provinces across the country. Some of the old Zoback papers sort of outline provinces, but we are seeing that what used to look like distinct province boundaries are actually more sort of gradual transitions and rotations that occur. There are a few cases like the Uinta Basin and Denver Basin I showed where, at least at the scale of data we have, we see what looks like an abrupt change. So I think that needs to be determined. And for the other part of the question, no, I don't think that there's that you can go from a phi all the way up to 3 and then go back around again to a phi of 0. And I think this figure should emphasize why that's the case, because the compressive states of stress are defined by having very high horizontal stress magnitudes relative to the vertical stress. So there's no mechanism for going back down to the opposite case where we have much lower stress magnitudes, horizontal stress magnitudes relative to vertical. Let's see. Don't have stress measurements from the Paradox Basin. Yes, I would love stress measurements from the Paradox Basin, among other places. And if anyone has data they'd be willing to share or point me to, that would be very much appreciated. How do you tackle the areas with scarcity of good data? Well, you can see places where we just simply lack SHmax orientations on the map. We are not filling those in. So you kind of have to interpolate with your eye in many of those cases. But for AFI values, we interpolated between places where we had focal mechanisms. The cases where they were quite uncertain, we have added some question marks where we were interpolating over very little data. And I think if I move to the uncertainty map, you can see what I mean by this. Oops, I'm going in the wrong direction. Sorry again. There it is. So the purple areas where we put the question marks have very low uncertainty. Or I'm sorry, have very low certainty, very high uncertainty, greater than 0.4 psi plus or minus in those areas. So we've interpolated, but we've put question marks there to demonstrate places where we just don't know very well. Comments on the leakage potential along faults, considering injection of waste fluids in carbon storage and geothermal projects. Yeah, I think that's a serious consideration. We see examples of potential fluid transport along faults all the time. The Fort Worth Basin may be a good example of that, where some of the wastewater disposal was happening significantly to the south of some of the earthquakes, say up by the Dallas-Fort Worth airport area, and it's been suspected that fluid transport occurred along those well-oriented faults, which tend to be the faults that are most conductive to fluids. So that's absolutely important consideration, and understanding the state of stress and the fault orientations is very helpful for understanding that. Orlando Ortega is asking, are there any considerations to keep in mind when we think about induced seismicity at the level of a reservoir or seal types of rock? Are all rocks at these stress conditions and scales basically behaving at the the same for each material, I think? And no, they're not behaving the same for each material. I have the maps that I've shown, particularly the AFE maps, are for the stiff rocks in the crust. So that would include crystalline basement, but it would also include sandstones and things like that. There's been a lot of work by people like Xiaodong Ma and Mark Zobak's group and others, Ankur Singh, on the viscous stress relaxation potential in some of these clay-rich reservoir rocks. So those often have different AFE values due to stress relaxation, we think, but we are not yet to the point where we can predict what that will be, but what the stress conditions will evolve to in those more ductile lithologies yet. The point about paradox basin observation is about consistency of direction with depth. Oh, yes. This is a question about basins that have evaporite deposits and how SHmax orientation or stress in general can differ both above and below that salt layer. Yeah, that's a very important point. I glossed over it. We see that in several places, or there are several places on this map where we have evaporite deposits. Most notably, the Gulf of Mexico, where we have the Luan salt down here, which is probably a detachment surface separating the states of stress in the sediments above from what's in the crystalline basement below. I didn't get into that, but actually, a lot of these measurements that we have in the Gulf Coast area are from right around the area where the salt pinches out. And so both above and below the evaporites in that particular case, we're seeing similar SHmax orientations. We are also seeing that in the Appalachian Basin area here in the eastern parts of North America, which also have evaporites. There was a nice study by Evans in the 80s showing the orientations of SHmax both above and below the salt, and they appear to be quite similar. That seems to be what our new data there are showing as well. But that's a very important point. Yes, stresses can change across salts due to the mechanical detachment that the salt provides. Okay, lots of questions here. Gary Prost is asking, for carbon capture and storage, is the CO2 dissolved in fluid or injected as a gas? In many cases, it's injected as a supercritical fluid. I think I'll just leave it at that because I can't say a great deal more about it myself, but I know in a lot of cases, they're putting it down there as a supercritical fluid. Anadita Dash is asking, can you please explain why the SHmax gradient is constant in reverse faulting regime? Yeah, that's quite interesting. The equations for this are laid out in the AAPG paper that is now a head of print paper on their website. And it's quite interesting. It's basically, the answer to that question is encapsulated in those equations. But for a given SHmax value, let's see, it's more easily explained, I think, with a Mohr circle, where let's say this is SHmax, and in vertical stress, the least principal stress is SV, and so the state of stress is constrained in frictional failure equilibrium by the Mohr-Coulomb failure envelope. So the size of that Mohr circle won't be increasing. Let's see. But in a reverse faulting case, as you get more and more compressive, it's actually, let's see. No, I'm sorry, I'm not answering that very well. The answer is also encapsulated in the AFE equations. It's the way AFE is defined as a ratio between the three principal stresses incorporates that change in SHmin increasing in that way. Sorry, that's just not a good answer to the question, but you need to look at the equations to explain it clearly, I think. What could be the best conditions for CCS? I think I'm going to leave that question alone and leave it to the experts. I would suggest getting in touch with people like Sherilyn Williams Stroud and others who work on CCS in a much more direct way. The Decatur example, I think, is a nice one, and there are others as well. Clinton Tippett is asking, is the crust pervasively fractured and faulted in all orientations, with the ones being favorably oriented being the problems, or are these problem faults the only ones in the rock mass? These rocks in most cases have had miserable long lives going through different tectonic events with stress directions changing over time. And so in most cases, unless the crust is brand new somewhere, say the ocean floor or something, we expect there to be a range of fault orientations. It's not going to be completely random. There will be fault orientations in fabrics associated with the tectonic events that have occurred there, but there will be many different orientations. And so we're expecting that in a critically stressed crust, it's the faults that are best oriented for failure. This is a good way to show it. It's those faults that happen to be best oriented for failure that keep failing over and over again. So it might be that there's no perfectly oriented fault in one particular place. So maybe the state of stress equilibrates in that area over geologic time with faults that are maybe not this red one, maybe just a little bit over here to the right, a little less perfectly oriented, but they're the best oriented in that particular stress state. But so I hope that answers that there's not complete randomness to fault orientations, but we expect there to be a large range of them. Let's see, what else is there? Okay, Anidita Dash is also asking, do the local stress orientations change post-major earthquakes? That can happen, yes. That's an interesting question. It has been observed in some places. I think it requires specific conditions where the stress magnitudes are similar enough to one another, say SHmax and SHmin are similar enough to one another that they can flip as one of them relaxes during the earthquake. Remember that earthquake stress drops associated with earthquakes tend to be fairly modest, I think tens of megapascals at most. So we're not expecting there to be, or in most cases, there's not going to be a drastic rotation of SHmax. There will be a change in the least principal stress as it snaps, as it's released, and the shear stress on that fault falls due to seismicity, and then they'll build back up again. But yes, it's been seen in actually a geothermal development case in Dixie Valley, Nevada. Steve Hickman, I think, published a paper on that in 2000. And Mark and students published a paper on same observation inferred for the Elk Hills oil and gas field in California. I think that's all the questions so far. If anybody has more, happy to answer.
Awesome, thank you so much. That was wonderful. There were a lot of really good questions that came through and you knocked them all out, so nice work.
There's one more, also from Anidita. What is the validity of the stress map that one could create? Is there a way of studying real-time stress variations? I think there are actually people doing this in plate boundary settings. It would require some extremely detailed, reliable data, and but yeah, it certainly could be done, and probably should be done where there's enough data.
Well, thank you so much. Thank you everybody for attending today. We really appreciate you, Jens, and this was very informative. I know you guys have some great publications out there, and we'll try to get this put on YouTube if we get approval. So y'all check back on our LinkedIn page, and we'll try to send out an email here later this week about our upcoming December speaker, Alyssa. So see you guys back next week, and thank you, everybody.
Thanks, everybody.
Thanks.